When do we start?
Yeah. Yep.
Now? Okay. Welcome, everybody, this evening. We have to discuss how to understand what the machine has understood. And we have here our list of panelists, Rémi, Shirley, Bhuvnesh, and Ben. So when I saw this topic, my questions were, what means understanding? What involves understanding of understanding? So I get a picture of your mind. And if your mind is an AI, do we need AI psychology? And I hope to get some enlightenment on these questions. Let's see. So our first speaker, is Rémi, and the stage is yours. Okay.
So, thank you, Torsten. Those are actually really hard questions, and I'm not sure we're going to be able to answer all of those today, especially the last one. But so, first, I want to say a quick thing. Yep. What? Oh, that's nice. Okay. So first, I'd like to say a few things. So I'm not an astronomer. I'm a machine learning researcher, but I've been working with on a few applications with astronomers. So when Torsten sent us the really hard questions, I wondered what could I say actually. So I'm going to tell you about some tricks we have in the machine learning community when we want to understand what's happening in our models. So the first step, maybe, the first step that's actually the most important one, you already all do it. If you want to know what's happening in a model, you want to challenge it. You want to know what is going to work on your data. And actually there is a comparison I really like about that is when you do machine learning, you're a teacher and your model is your student. And at the end of the year, well, you want to know what your student understood about your course. So you're going to design an exam, and hopefully a smart exam, so that you evaluate if your student actually understood, instead of if they learn by heart, you know, the answers of the question. And in order to do that, you're going to have to look at the performance of your student. Can they solve a problem? And a really important aspect here is to look at what happens to the performance depending on where you are in the space. The good example is you're going to do the exercises for different parts of your course because you want to know that they learned all the different parts. Okay, so one example here. So in a quick. Okay, so here, in the collaboration I did for strong gravitational lenses is we wanted to see the performance of the model as a function of one of the parameters, that is here the Einstein radius of the lens. And you can see that the model works better around 2. It begins to fail for small radius, which is, of course, more difficult. But the comparison with the human was really interesting, actually, because this is human visual inspection, is classification by a human. And you can see that when the human kind of fails for small radius, the machine still works. Okay, so it's one way to say, maybe in this area, maybe we can trust the machine, this kind of thing. And then you have to understand what's happening. So we've seen a lot of plots with TSNE embedding. So that's one way also to see what's happening inside your model. And maybe the most important one that's actually a bit recent in machine learning is, can I break it? Can I break the model? Can I attack it? And how will it fail? You know? And that's actually what we call adversarial example. And the idea is, you know, the tricky question in the exam. Okay, you're going to do an exercise that's nearly exactly the same that you already solved for them, but you're going to change just a little bit of things. And basically, those who understood can obviously solve it. Those who cannot, won't. Okay, so that's the first part, challenge your model. The second part, and now we are going a little bit away from the student example because you're going to do awful stuff to your model, is make the model explain itself. So try to understand what's happening inside, and for instance, you can look at what are the important features. Okay, so there are methods, well-known methods in machine learning, such as feature importance, that tells you, oh, this feature has a large impact in the decision over the whole data set. You can also look at what's called partial dependency plots, in which you're going to see the effect of changing one variable in the final prediction. And of course, ablation studies. I've seen a lot of those actually in those presentations, where you're going to cut part of your model and look at the performance when I cut it. And you're going to see, so this part is important because it's going to bring more information, a better performance. But those are all global strategies. You can also look at more precise part at one given prediction. You're going to take a sample, you're going to predict with it, and you're going to try and understand what happened. So what were the important variables to make this prediction? Okay, so this is related to saliency map. It's going to tell you, for instance, this variable, if I change it just a little bit, this variable is going to have a huge impact on the final prediction of the model. And this is one way also to understand what's happening. And you also have more higher level, maybe interpretation model, like the SHAP and the LIME, that are quite nice way to interpret the output of a CNN by telling you which part of the image actually helped reach this prediction. Okay, so for instance, if you want to classify a gravitational lens, you can check that the model actually looked at the lens and does not classify the background because you have a bias somewhere. Okay, great. So this is step 2, and up to now I gave you methods that we use to understand a model that's already trained. Okay, you already have it. But actually, step 3 would say, well, let's design the model to be interpretable. Let's design the model so that we can better understand what's happening there. And, well, the simplest way to do that is to have a model that you understand. So, I mean, I always say that, and it's really important. If you can keep it linear models are easy to understand, and well, you can really interpret, say, and explain the decision. Of course, in numerous applications, you can't be obviously linear, but if you need non-linearity, especially in images, try to keep the structure. Okay, that's why all those fully convolutional architecture work so well, is because they preserve the structure of the image, which means that in each of the layers, you're still going to have images, and you can look at those images. So a quick example here. So this is a neural network, a convolutional neural net that they designed to deconvolve, to reconstruct observed image. Okay, so you can see that as super resolution. And if you look at the representation of the image at the different layers, so the first layer is really simple, like, you know, gradients, low pass filtering. But when you begin to look at the second layer, where you have non-linearity, stuff is happening, and you can see two different kinds of images. So you see the large object on some of the activations, and on some of the other activation, you see point object. So in other ways, in order to reconstruct the image, the neural nets manage to separate those two sources and treat them differently, because, well, they have different properties. And that's where the nonlinearity actually helps you. And that comes to the last point I want to make. If you want to design it to be explainable, I mean, you already know a lot of about the physics here, and most of your data, when you train actually, is simulated. So you have information, you have additional information. So maybe one way to be interpretable is to use what is called a bottleneck. A bottleneck will basically use, well, a black box or a neural net to encode your information into attributes that make sense for you. Okay, so basically for you, those attributes would be descriptors, you know, the size, mass, this kind of thing of the objects, okay? And then use a last layer that is simple and easy to interpret. And when you use this bottleneck, you might lose a little bit of performance, but you're going to gain a lot of interpretability, because you will have the output. And I mean, if you use a simple model here, basically you can say, oh, I'm going to predict this because this attribute at this value, this attribute was activated. Okay? So making it explainable by design, you're going to have to design yourself your nets. So last comment. Right now, we are doing a lot of research about interpretability, but I mean, let's be frank, you're still going to get a black box somewhere. Okay? So even here, you still need to have the embedding here. Okay? So what I'm trying to say is you still have a black box. Take some time validating, looking at every possible ways how it works so that you can at least trust it a little bit. And small comment, so I've seen 2 really interesting presentations this afternoon about domain adaptation. I think that's a problem that actually most of you have, is that you're gonna have a simulator that gives you a lot of data so you can do deep learning, but then you're gonna apply it on real data. And that's the domain shift problem, what I call domain shift. And it's a fundamental problem. We are still trying to do something about it in machine learning. So there are numerous methods to try and maybe not solve that, but compensate a little bit for that. And I mean, keep it in mind, because even if you understand what's happening on your simulated data, well, if you have to adapt, if the properties of the data change, everything you thought you knew might change. Okay? So, well, that was my last point. Thank you.
Thank you. We also have a change in the way we do this. Today, we are taking questions after each presentations and have a little bit debate. So you don't have to remember what people say for so long time. You can ask directly. But of course, the question is to the full panel, right? So not only Rémi can answer. So do we have someone who wants to ask a question at this point? Maybe let's wait a minute. Yes, please.
Hi, Sotiria Fotopoulou. I wanted to get your opinion on the SAP and LIME methods, because what we are doing there practically is we are approximating the model, right? You're not asking the model you train, but you're trying to approximate somehow what you have learned.
Sorry, what method?
LIME. LIME and SAP.
Yeah. LIME is here to tell you which part or which variable, okay, of the image were actually important for the prediction. They're not going to tell you the value or anything, okay? It's just going to tell you focus here because something happened here that led to this decision. So it's always a partial, anyway, a partial observation. But it's interesting because it won't tell you everything, but it will help you detect when the model has a bias. As I told you, if you detect an object and you check with LIME and you don't activate the area in the image where the object is, it means that you do have a problem. So actually it works, but you don't know how. And that's the worrying part.
Okay, someone else of the panel wants to say something about that?
Maybe I can just make a comment. This meshes really well with the discussion of model incompleteness and model error and how to deal with that. And sometimes you're lucky and the systematics sort of live in a very different space from the signal. In that case, you can have more generic approaches to try to introduce degrees of freedom to absorb the systematics. But of course, in general, it's a very difficult problem.
And do we get any feedback from the remote people? Would we recognize if they want to say something? I just want to make sure that if they want to say something that... Shirley wants? Yeah, please.
If that's okay. I'm curious, you said that it will always be a black box. Do you think that it will always be for a very long time or just for right now?
Well, it's always hard to predict the future. For a long time, it's going to be a black box. I mean, we are just starting to have, theoretical results about what's happening in those complex neural nets, and still not yet, for the deep ones. So it's, I don't know. I think it's going to stay at least, deep learning, for a while.
If I might add, I liked very much your statement about putting our knowledge into the networks. And I think Peter's talk this afternoon showed exactly an example of that case.
Exactly.
Right? Having a representation of the full rest frame spectrum of a galaxy, even if your data is only on a single thing, is a step exactly in this direction. Okay, more question over here, please.
No, I was wondering.
And name.
Mark Huertas Company. I was wondering if it's actually a lost battle in the sense that there is a trade-off between accuracy and interpretability. And if we are using models of millions of parameters, can we actually, hope to understand these millions of parameters? Or, or at some point the avenue is reducing the models, but if we reduce too much the models, then we lose accuracy. So.
Again, a really hard question. So, yeah, I mean, you have millions of parameters. You can't really understand everything that is happening. And that's what we see in those adversarial examples, is that basically you train on your data. You're going to have parameters that works well on your data. And if you just change a little bit something, it's going to explode in terms of prediction. So clearly, we're missing something. Still, from what I understand, recent results tend to say that out of those million of parameters, in the end, just a few of them, not all the parameters are useful at the end. So it's not, you have a lot of degrees of liberty, but you don't use all of it in practice. And that's how the neural net do not overfit, actually. So, yes.
I mean, if you take this really far into the future, and then we could imagine that eventually we'll get neural networks that, I mean, we could speculate that neural networks might outperform anything that a human being might possibly be able to do. And in that case, then how do you make that interpretable? I mean, if at some point there's going to be some conflict between interpretability and performance, like you said.
If you can do the task yourself, how can you ask the method to explain itself to you?
But perhaps one interesting avenue for research is in that particular moment we are now is trying to find the simplest model that can get the best accuracy. And I don't know if, because that would be the simplest interpretable model by definition. And I don't know if you can comment on techniques that do that. Do they exist, or how mature they are?
Yes. So there are techniques that aim at doing approximation. So you basically learn a really complex model with tons of parameters that works well, and then you try to fit your complex model with the simplest one. Okay, so this is called distillation. It's been investigating for several years. It's a really, really interesting, machine learning field. So we have things that work, but you're always going to lose a little bit, and so the question is how much I'm going to compress, and usually people just don't want to compress as long as it fits in the GPU. Let's keep.
I mean, Shirley's going to. I think we'll probably talk about. I'm hoping we'll mention some of her work along those lines.
I think we should go on with the panelists. Really.
Booth has raised hands for a while.
Booth has a question.
Yes. Please. We still have time, right? If you 10 minutes.
Can I make a quick comment? So I understand, Rémi, that you've been talking about interpretability and black box in a certain sense about the machine learning algorithm. But could we not open the black box somewhat just through brute force experimentation? In cosmology, we have, suppose you're interested in less than 5 physical parameters and are worried about less than 10 conflating systematics. You could just run, thousands or maybe millions of simulations that probe the combination of these effects to see what the network is learning. And this, of course, touches on the question of, will we trust the result? It's a way to convince yourself that it's not a systematic masquerading as a physical effect.
Yeah, so I agree with you. By brute force, you could sample your whole, hopefully, function by the model and try to interpret it. But as you said, you're going to stick to small dimensional problem.
Yes,
of
it's
course.
by no means an elegant approach, but it may be what we are forced to do.
Okay, I think we still have time for another last question before we go to the next presentation. Is there something online? Or Bhuv, you want to add something?
Sorry, no, I'm done. I'll lower my hand.
Okay. So, yeah, then I propose we have Shirley now.
Sure, I'll try to share my screen.
Yeah. So
I'm not trying to answer all the questions, but I will have a very biased perspective for fun and just to be provocative. Can you guys see it? Yes. Thank you. Hi, everyone. I wish I'm in Paris with you guys. I hope next time soon we will be able to do it. I like the topic of the discussion today, like what can we understand, what the machine understands. Well, I miss an S here. I'll give a very biased perspective based on some of the work led by my students, Miles Kramer, and also some of the work, I think some of the participants actually here, Pablo Lemos, now Jeffrey, Peter Battaglia from DeepMind, Alvaro Sanchez from DeepMind, also Rio Su, also students from Princeton, and David Spergel, who's the Simons Foundation president now, actually. And what we've done is trying to train a network and, just say what's going to decide what to do and predict what happened next. So it's just a bunch of planets moving around, and we try to go from time t equals to 0 and time t equals to 1. And then we say, it seems to train okay, right? So the top is the truth, the bottom is the predicted. It's 1,000-step rollouts, which actually means we're only training it with one time step with this architecture graph network. And a specific version of it is called interaction network. And this one time step we're trained only just one time step, but then you keep rolling it out, which means you take the predicted output and feed in as input and let the network predict the next step for 1,000 steps forward. So you can see that the n-body simulations do pretty well. The balls bouncing forward is actually one of the hardest ones because it's so chaotic, like a small difference in our projection output will actually cause these like huge differences later on. And then the springs on top of this mass look okay. That's pretty surprising. It's I was kind of surprised that it works quite well because it is accumulating basically errors for 1,000 time step, with each step being processed by a neural network. And then this is a zero-shot generalization to larger system, where we have not trained the network to see n-body system with this large number of planetary systems or a large number of balls of this long string. And you can see that the truth on top and the model below looked pretty good. Not perfect, but given that it's never seen this kind of training set before, it basically has never seen this large number. We trained it with several different numbers of, say, for example, different planetary systems, up to, say, I think 10 or 11 planetary system, for example, here, and then we just went to have bigger ones. And it still works quite well. So we ask ourselves, how did the network figure out this, right? So taking a tiny step back, what did we do to get the network to predict the dynamics correctly? Is that we take this data set and we feed it into a graph neural network. And this graph network did super well. For those who are, specialists in this area, we use the interaction network by Battaglia et al., which is a collaborator in DeepMind from 2016. And there are improvements over that since, and it works, as you can tell, pretty well. And then we did something kind of cool, I think, which is to use symbolic regression, which is, for those who know this, is actually part of the genetic programming. It has been around for a long time. It is basically a search of equation space. We use symbolic regression to basically try to understand a piece of the network, just pluck it out, just the edge function of the network, what the function is actually doing, and also the node function. So for those who haven't done graph network before, the nodes are described, these are nodes, and these are the edges. They can be multi-directional. They can be unidirectional or bidirectional. And each node can represent, different properties of, here would be like the mass and the positions, for example. And the edges, we don't know what it represents, but for the scientists in the crowd, we probably expect some kind of forces. So what we did is that we took basically this network, train it, run it, and then you encourage a very low dimensionality representation at the edge function and the node function, and try to interpret what they are. And we use symbolic regression to basically extract that equation. So like, do we find this equation in the end, right? That's the question for this particular case. So we just want to show there's some kind of inductive bias going on here because the graph network looks very similar to Newtonian mechanics in the way it's set up. So you have a bunch of nodes and you have the input state, these particles moving around or planets. And then the pairs of nodes are like two interacting particles or planets. The edge models are sort of like the forces. And you have the messages, then you actually pull them together where you sum over altogether for each of the node. You get a net force from all the messages that is receiving from all the other node, right?
5 minutes left.
And then in the end, go ahead.
Sorry.
Is that
5 minutes?
Yeah, that's totally fine. Don't worry. And then in the end, we actually get an acceleration that you can imagine the node model will be calculate something like acceleration and compute the next time step, and you check whether it fits. So then we thought, okay, so this looks so similar. We should be able to figure out what these edge functions were doing and what these node models are doing. And that's what we exactly did. The cool part about here is to realize you can take all these, edge functions and you say, okay, let's try to regularize it to make as small number of elements that are relevant as possible. And what we did a bunch of different regularization and realized that given the input is only 2D, we try to have 2 dimensions for the edge vector, which is turned out to be very difficult to make the training work because there's actually noise. And we end up using L1 regularization to minimize the number of message elements that are important to fit the observables to the predictions. Then we put the edge elements through the symbolic regression that we talked about and see what would fit for the 2 elements. And we were very surprised and also quite happy to find that the edge function of the network is basically a transformation of the force laws for the following systems. We showed the Springs laws and one of our R-square law in 3D. So we were quite excited. And I want to be sort of provocative here and say, with this help of inductive bias and the symbolic regression, we were able to find out what the edge function's elements were doing, actually also the node function in this case. This is still a very specific case because we need to be able to model a system with graph network, and the edge of the network are all doing the same thing and only need very small number of elements to describe. Can we sort of push this idea further, interpret, say, other learned network, first like a much more complex graph network, or maybe other types of network? So I'll just sort of like leave it there and be a little bit more provocative and see what people think that we can maybe interpret the black box a little bit more.
Thank you. Are there immediate questions by somebody? You? No. Ah, sorry. Or by the other panelists.
Yeah, this is amazing stuff. Shirley, where do you see this going? I mean, what's the next step? Where in your wildest dreams, where do you see this going? And what's the future for this?
In the wildest dream, I'll be retiring in a camper van in California. But that's the wildest dream, personal ones. For this one,
just before that.
Before that, it will be nice to be able to. So right now we have graph network, which are quite close to the system what we are trying to interpret, right? And the graph network itself so similar to this particle and has a strong analogy to the Newtonian mechanics that we end up learning. So in this case, simpler, I think, to interpret the network. And it's a very simple network when you look at it. So I think, and then combining the symbolic regression with it makes it possible to search this equation space that interprets these elements, these edge elements, or node elements with these functions. I'll be very curious if we, first of all, make the symbolic regression search also part of the stochastic gradients that we're searching already in the network. Right now, it's done in 2 different pieces. So doing the same optimization will be really efficient. Second is, I think Rémi talked about pruning or distillation earlier. And I think it is somewhat related to this, where if you can prune a network to make it really, really sparse, say, I don't know, right now we're pruning at, say, 40% would be like dramatic. And if you can prune it so much, there are only, say, hundreds or thousands of elements that are actually important, then the improvement on the symbolic regression on the search side might actually allow us to interpret what these, or at least find a function, I shouldn't say interpret, find a function that tells us what the predictions depending on these, say, thousands of elements or hundreds. That would be the next step. But then you're saying, okay, can we understand it? Which I think our chair had asked really hard question. I think having a fitting function doesn't mean you understand it. I mean, this is a very special example where things are simple, and it might not be something that we can always interpret and understand. And so that's why we need all the scientists to come in to say, okay, for this predictions, and we have this fitting formula, why is that the case? I think the understanding will still need a lot of work if we need the machine to present us an understanding.
Can one use the techniques Rémi was presenting in order to understand these networks better? Like,
I mean, she already did an amazing job here.
Yeah.
With the symbolic regression, as a last step is extremely nice, because you have something that is extremely complex, but in the end you're going to simplify it so that in a function that you can actually look and understand. So no, I mean, you did. Yeah, I agree. It's strongly related to distillation. I think it's a really elegant way to solve this and to try and find the relations. But I had a small question then, because I have the microphone. So I find it extremely interesting, and I was wondering, as a machine learning guy, how it's going to scale, because when you talk about masses in space, your graph is actually dense. You can't use L1 here because all the mass has an impact, even small. And so is it, I mean, do you have ideas to scale it to large, with lots of nodes?
So we actually ran into this problem, what Rémi was talking about, where the L1 regularization is not enough. So we were trying to learn basically learn the equations in the turbulent simulations. And it has a lot more components than, the simple F equals to, GM1, M2 over R squared. It has way more elements. And it turns out that we have to have a special, we have to change how we regularize it dramatically before we can get to the equation. It's not perfect yet. There are, this is something we're working on, so I wouldn't go further into it because we don't know the answer. But I think there are ways we can do it, and regularization techniques is a huge field. So I don't think we've scraped the surface yet. Even like there are all the techniques that we can try. So I'll be very curious to hear what others think, what the regularization techniques we should try. We're also working with Nathan Cuss and Steve Brunton on using some of their techniques in helping with the regularization and the optimizations.
I knew you would ask.
Hey, Shirley, thank you. Do you think your graph neural network will be able to discover GR?
Pablo should answer that. I think he might be in person or virtual, but Pablo actually led this work, which I didn't show, but I would love to show another time, which is they took the same architecture that we had, actually we all work in the same team, and used real data from NASA. So there was 30 years of NASA Horizons data for orbiting all 30 years over, this whole, about 31 bodies. There are planets and moons. And our original goal is to discover GR. But it turned out that GR, the effect is so small that we end up discovering, Newton's law with an error bar that is large enough that, GR can probably fit in. But, that's what happened. And we actually did use real data and discovered, well, unfortunately, just the Newton's law. But it's still pretty cool that we got all the masses right. Yeah. So you have orbital data, which you have no masses at all, just positions, and you got the masses correct. Except for those who have very light mass within the system. So those have larger error bars for sure.
Just to comment on that, yeah, we're trying with the GR as like a perturbative thing. So like we know Newton, can we learn a perturbation? I suspect that there's going to be noise and kind of missing bodies that are more noisy than GR, because it only affects one of the many bodies. But what, I mean, you also would only learn like a correction to Newton gravity, not like the kind of beauty and geometry of GR. So I guess that's, again, where the scientist needs to come in and interpret. But.
Yeah, you might discover Vulcan first.
I mean,
directly to this, Ben?
Yeah, as a more general point, if you are modeling, so in this particular case, in the setup, there was a simple law to be learned, and it's amazing that you can actually recover it. If you're going to a very general system that's quite complicated, and you imagine scaling up an approach like this, there's no guarantee that there is actually something simple to be learned. Maybe you can find a neural network that is able to predict a complicated system, in the rollout, for a long distance, long time into the future, but it may actually not be easy to interpret. But I think this approach is still extremely valuable, because sometimes you might get lucky, and there may actually be a simple thing to discover that you didn't see immediately by looking, and the network essentially helps you search through all the space of possible explanations. And ultimately, if there is a simple projection, then this kind of approach might be able to help you find it.
There was a question over here, or a comment?
Hi, it's Conor O'Riordan. Yeah, that's a really interesting technique. I was just wondering if you've tried it on some kind of system where you don't know the underlying physical law, or maybe where there is no underlying physical law, and maybe is there some sort of blinding in the technique to make sure you don't just find what you already know is there?
Great question. That's actually in our paper. We got asked by the referee the same question. So we went and did something we don't know the law, we still don't know how to interpret it. We actually looked at try to predict the central density of halo based on its surrounding environment. And it turns out to be, a formula that we did not expect, but it makes really good predictions. So we have a law that I don't offer understanding, I can give you a fitting formula. So that's another situation that had happened. We also apply similar things to sort of the mapping between dark matter and galaxy properties in dark matter and galaxy number density. And that's the work led by Jay Wadika, Anna Marie Delgado, and also Boreana from Harvard. Jay is actually at IAS right now, just moved from NYU. And they also have been using the symbolic regression formulation to discover these extra terms of the dependence between galaxy number density and dark matter halo, not dark matter, halo properties. And it's, we don't offer explanations, we just offer fitting formula, I have to say. I hope scientists still get a job afterwards.
Okay, let's get the next momentum from Woof. So let's get to his presentation. So we still have one question here. Okay, let's, if you permit, we squeeze in one question.
It's more of a comment actually from Slack, from Peter Melchior, who is addressing to Shirley and Benjamin. He says that you mentioned the equivalence between the GNN setup and Newtonian forces. It what makes this work. And it said that the GNN plus symbolic regression works in a much wider regime. It's the inductive bias from the graphs that will work whenever there are interactions among an unordered set of items. He also said that, as an example, we've done work on resource allocation in very complex systems where the items negotiate for resources like observing time, for which we definitely do not know the formal solution.
Yeah.
That's a great, actually, thing to, also led by Miles Kramer's work with Peter. So it's just really great that Peter mentioned this.
Yeah, I mean, the deductive bias is about the pairwise interaction. Didn't mean to say that somehow you put in Newton. But the pairwise interaction is the thing that pulls it out.
Okay, so let's move to Woof. Please.
Thank you very much. I really enjoyed Lily's talk. Let me get started with mine, and I look forward to the discussion. Slide looks okay? Okay, I'll assume that's the case. So I'll describe a case study from weak lensing, in particular, looking at the quasi-linear regime and the three-point function. So Shivam Pandey is my graduate student at Penn, and with him and Marco Gatti and Cyril Du, we've had a lot of discussions. Also Lucas Sacco, Chi-Wei Chang at Chicago, Mike Jarvis at Penn, Elizabeth Krauss at Arizona, who's in Paris, and Masahiro Takada in Tokyo have been my collaborators on some of this work. So you've heard about saliency maps, and they may be useful to unpack deep learning, and it's worth discussing applying them to just direct images, galaxy morphology or time series data to find objects, and also to science images like lensing mass maps of the kind I'll show, and possibly to summary statistics to see what we can learn and whether they can help solve this worry of some mysterious systematic is degenerate with neutrino mass and the deep learning network gets fooled. So in this picture, this network was very good at classifying boats, but things like the saliency map showed that it was actually relying on quite a bit on the water, which happened to be in nearly all the training images. So it might have had trouble with boats on land, things like that. I won't talk more about this, but we've had some great discussions. I want to talk a little bit about understanding. It's really hard once you move beyond the linear regime and two-point statistics of cosmology. I've only been working on this for 20 plus years, and I have almost no physical understanding of the things I'll be talking about. Three-point functions, Minkowski functionals, peak statistics, this whole universe of non-Gaussian statistics. I think we know some of the math, and most of all, we measure them from simulations. So that's what gives us confidence. So it raises the question whether we'll trust some deep learning result well before we can understand what it does, either in the sense that Rémi was talking about or in the sense physicists like to think they understand things. So when I talk about machine learning, I'll mostly have in mind a field-based, convolutional neural net kind of approach. So let's ask what it is we want to understand a little more detail. Do we want to understand in cosmology how cosmological parameters are being inferred? Or do we have a particular question in mind, like comparing the early versus late universe observations, where there seems to be some tension? Or are we pursuing a new physics signature, like SIDM and galaxy halos, which may be more amenable to understanding if some deep learning network applied to the details of strong lensing images tells us something about substructure not being CDM-like? There's maybe better hope to understand that than some broader cosmology analysis. But I'm going to stick to cosmological parameters. And we can discuss numerical simulations, which I commented on already. But for now, I will stick to this quasi-linear, analytically tractable regime. And to pose this question, can we estimate how much of a deep learning constraint comes, say, from the three-point function? So, you smooth the data almost always in cosmology and definitely in field-based deep learning approaches. And there's a lot of detail in that smoothing where there are hidden dangers. But let's set that aside and say that as a first step, we are able to smooth out all small-scale structure. So we are talking, leaving information only on scales of order 10 megaparsecs and above. And then one can hope that a deep learning approach will reproduce 2 plus 3-point constraints. I'm also implicitly assuming higher order correlations than 3-point don't have a lot of information in this quasi-linear regime. So can we go further? Can we develop a controlled program of adding in small-scale information in bits that we can understand using our menu of non-Gaussian statistics, higher order correlations, peaks, topological statistics? Because if we can project what a neural network is learning onto those statistics, then that's, you know, a massive confidence booster. And it's not the same thing, because we know that in practice, it's proven really difficult to deploy a whole suite of non-Gaussian statistics. So a deep learning network that is almost redundant with them would still be massively useful. Okay, so here's my case study. This is the dark energy survey mass map. Elizabeth Krauss gave you an excellent overview of our the current state of our survey and all the results from it. This mass map was presented in 2 papers led by Marco Gatti and Niall Jeffrey. This is a new result that is contained in a paper that appeared on the archive this morning for you. And it's a paper led by Marco Gatti, shown here, along with a number of DES collaborators. So these are contours in sigmoid omega matter using the 2-point function shown in red and the 3-point function shown in green. So we are very excited about this result. The 3-point function is weaker, but it adds non-trivial information. In gray, you can see the joint constraints, which are, you know, significantly tighter than the 2-point constraints.
3 minutes.
Is there a question?
I said 3 minutes roughly left. I just wanted to add.
Okay, thank you. I might take a few more than that. You know, one kind of surprising thing is that the third moment by itself, even though it's weaker than the second moment, is in 2.8 sigma tension with Planck when you look at the tension in the full parameter space. So there's a value in having these complementary statistics, which are affected by, in this case, many systematics much more weakly than the 2-point function. So, of course, the net tension of the joint constraint is still below 3 sigma, but it sure seems to be not disappearing. So, about understanding. You know, 18 years ago with Masahiro Takada, we had worked out both analytically with the Halo model and from ray tracing simulations, a bunch of these 3-point functions. You get 4 of them that carry the signal, and this is for an isosceles triangle. You can see this rich configuration dependence that is characteristic of gravitational clustering. Shirley may not remember an undergrad paper she wrote on this topic as well. And now for the first time, it's taken 18 years because we needed enough data. We have a measurement of this. This is from a paper in preparation led by Lucas Secco of this configuration-dependent 3-point function. We compare it to simulations. Everything looks sensible. We can break down where the signal to noise is coming as a function of angle. So both in testing the physics and in testing robustness of systematics, we feel we have a handle on it. So I was exaggerating slightly when I said we don't understand a thing about non-Gaussian statistics. These are some of the limited things we understand, and they're quite powerful. But it took, you know, this is, I won't describe in detail, but this is like, you know, signal to noise of 13 in one redshift bin. It took a pretty high signal to noise measurement, which we've only gotten now to be able to do this. Pushing further into the nonlinear regime, there's a paper led by Dominic Zurcher on shear peaks. But our subject today is machine learning. So I'm aware of one paper led by Janus Fleury from a few years ago on the kids survey, where they compared power spectrum constraints with CNN constraints on a similar lensing survey, the KID survey. And you can see that all these non-Gaussian or machine learning approaches, although completely blinded, have given us constraints that are in the ballpark of what we expected, certainly consistent with our 2-point constraints. So that's one possibility, that a deep learning approach will kind of sneak up on us, and it'll become part of conference discussions just like this one, and it will be more powerful than our other methods. So what are the lessons we've gotten? From this 3-point analysis, it takes a long time to develop a reliable machinery to do cosmology. And although we used analytical methods, simulations are indispensable for doing the computation and for doing the robustness tests. So the check mark in the first item says the same thing is going to hold for some pure machine learning approach. Here, doing a robustness test with simulations is a program that is to be determined. Many of the first steps are clear if you think about them, but it's a long one and it has to be carried out. For the 3-point function, these analytical tools give us a bit of physical intuition. Like the halo model tells you which halos are contributing, perturbation theory tells you which scales are contributing and which part is purely analytic and so on. I don't know that such tools can be developed, some kind of sanity check tools for deep learning. And then another program that is to be determined is to what extent we can project out the information gain onto summary statistics that we know and love.
Bhuv?
So my last slide. How can we validate, how can we validate something like CNNs as precisely as we validate 2-point statistics? This is a serious worry. So far I've been a little glib and optimistic, but this is a serious worry, and there's a lot one could discuss. There's another practical point that, as test cases, we are doing lensing only maps and stuff. But meanwhile, 2-point cosmology is mixing galaxies and CMB lensing and SZ distortions. And we are recently, there's a 13 times 2-point paper by the Zurich group. So how will machine learning keep up with this multi-wavelength, multi-observation era remains to be seen. Nevertheless, I have a prediction that in less than 5 years, we will have reliable cosmological advances from deep learning, and the understanding may take another 5 years.
Thank you.
I will leave you with one slide, that I've been discussing with some of you and with other colleagues, the possibility of a challenge for machine learning, starting with weak lensing.
Yeah. Why don't you leave this up?
Happy to discuss this.
While we start, why don't you leave your slide up while we start taking questions? Is this okay? Thank you.
Yep.
Yeah. So we have a sentence of the day, and the sentence of the day from Tuesday, that was Elisabeth Krause by saying, we want to be blind but not dumb. Well, I don't want to be blind, but that, and you made the sentence of this day, I believe, which is, understanding is overrated. Is everyone agreeing to that, or does someone wants to argue with this bold statement? The floor is open for questions and discussion. Ben, is understanding overrated?
It's not coordinated or anything, but I actually have a slide on a very similar point later on.
Okay. Spoiler, do you agree or not?
Trust is not the same thing as understanding. That's
okay. What is the difference between trust and understanding?
Wait for my talk.
Okay. We can have it right now, right? Unless someone asks a question.
Since I made essentially the same claim, I can tell you the sense in which I made it, that I would trust a CNN result, because if I said I trust a CNN result, that means that a completely independent group using a completely independent methodology, I believe, would produce the same result. So reproducibility is one element of trust.
Mm-hmm. Reproducibility in what sense? You mean with the same architecture, with the different data? I mean, that's the hard part.
I mean, in the step-by-step, most of my talk was very old-fashioned and boring, 3-point correlations, quasi-linear regime. So in that step-by-step approach, you reproduce one part of the result using known non-Gaussian statistics. You reproduce another part of the result with some completely different architecture. So I guess what I mean to say is that, we can sit here and say, oh, I trust, I don't trust, or I don't understand, but the community moves forward. And if multiple groups who are known to be decent scientists start to produce similar results, they will get taken seriously, whether you like it or not. So that's sort of the pragmatic sociological point.
That's a very good point, but actually in machine learning, we have this huge problem about reproducibility right now. We have challenge of reproducibility. Some papers, people just can't reproduce their performance, even on the same data set, using the same architecture. So that it's going to be hard because you even have more constraints. The physics is here for you to... That's what I'm saying. So, of course, open source is going to help.
Absolutely, I agree. It's very hard.
Yeah.
Hey.
Please.
So reproducibility is part of the basic scientific process and scientific method, so we can't get away with it anyway. But on the fact that understanding is overrated, I think it depends what question you're asking and what problem you're addressing. If we are here to understand the universe, then understanding is not overrated. If we are trying to fit a function and we find something that works well, then understanding it's overrated, it works, you're fitting a function. Go ahead, right? So it really depends on what the question is.
And what is the criteria to decide between these cases?
I mean, understanding is always up to some point, right? I mean, I think everybody here would say that they understand Newtonian gravity. Okay, but you don't understand gravity, right? Maybe you understand GR, but you still don't understand gravity because we know GR is not the final answer. And actually, if you dig a little bit deeper, you understand nothing. You don't know how gravity works. It's some emergent thing. Maybe there's some quantum microphysical thing underneath. So the desire to understand will always be there. And that's a very good thing because otherwise there wouldn't be science. But understanding will always be limited at some point, ultimately. And we have learned to live with that. So that's maybe another way of saying understanding is overrated in a much less provocative way.
So you're saying there are pieces we have to trust on, and so we can't understand everything at the same time. That's the direction.
Trust in GR has worked really well for people. It's a really.
Let me give a concrete example to respond to Lichia's excellent comment. You take the finite neutrino mass. Of course, if we make a detection of it, then the physics is the thing we're all after. And if you look at the power spectrum, we have a very clear intuitive understanding of it. It suppresses the power spectrum on medium and small scales. But it also does other things. It subtly changes the structure of voids. It diffuses out of large-scale filaments. So whether it's a non-Gaussian statistic we already are comfortable with, like Minkowski functionals, or whether it's a deep learning network that picks up these subtle features, we won't be able to pinpoint what it did. And so that's just an acknowledgement of something that I think has already been happening with statistics that we are comfortable with, and that'll happen more. I'm not saying it's fun or comfortable, But I am saying that reproducibility and trust is likely to come before that kind of physical understanding.
Okay. GM?
Yeah, so it's related to one sentence that you said once, Ben, about like science advance one funeral at a time. So can we say the same thing about understanding?
I hasten to add that was a quote as well. That's not my invention. That science advances a funeral at a time. That's more sort of a sociological statement. No, understanding. Trust. Well, understanding. I don't know how understanding advances. It's a scientific process. It seems to have worked quite well, and we have theories that work. And at some point, we understand the theories, but that doesn't mean we understand everything. Right? There's always going to be the next level that we don't understand. The quantitative description of how trust evolves, I think, is much, much simpler, and that's something I will discuss later.
So last word.
Yeah, just so trust but verify. And then second point, I guess, it's nothing so mysterious, though, that this is Henry McCracken, by the way. It's nothing so mysterious. Understanding, right, you have a model which reproduces the observations, right? So Newtonian gravity still works pretty well in a certain set of circumstances and for certain sets of parameters, whereas GR is a better theory because it can reproduce more observations. So understanding should just be how well can you reproduce what you observe in the universe.
But if you drive your car with Newtonian gravity, you're going to, and using GPS, for example, then sure. You're going to have lots of accidents.
Yeah.
Okay. So the last momentum talk by Ben, who is telling us what is understanding. Please.
So can we have my slides up? Let's move. Okay, so I would just want to make a few general and a few technical points that pertain to understanding by neural networks or machine learning techniques in general, and how that relates to human understanding. Yes, like this? Oh, my hand higher. Like this? Okay, thanks. So an observation really of what's been happening at this conference has been that it seems like there's sort of two levels of enthusiasm for machine learning here. And I'm not saying two camps because the second level of enthusiasm is a superset of the first. So one is to say that you have machine learning for quantity. So we'd have large data sets, we have to get through them somehow. Maybe we can train these machine learning workers that will do things for us that we can't do with human workers, and it'll just take too long, and because they're trying to be fast. And so, for example, we talked about classification tasks. Mark was talking about that. And if you make a few errors, it doesn't matter because you can recheck. Of course, you could also ask, why are we classifying at all if it doesn't really matter if you make mistakes? But it's definitely true that, and that's very similar to how machine learning is being used in industry as well. If you misclassify some cat as a dog, it's not that bad. But there's this next level, I would say, of enthusiasm for machine learning, which is machine learning for quality. So, which is still somewhat aspirational. The hope is that somehow we'll be able to use machine learning techniques to transcend what humans are able to do. For example, in terms of extracting information from about physical models from some data set. This debate is probably more about the second aspect here, because that's where we would like to understand what this next level machine learning tool is telling us. And we're already in that regime at some level I talked about on Monday. machine learning giving us estimates from hydro simulations where we don't really know how it extracts information, but we observe that it finds information on scales that we might not have suspected the information to be. So there's going to be some surprises, and we need to understand those surprises. That's the desire. So there's something that we have in common with the machine. Human understanding, like machine understanding, is usually about finding lower dimensional or low dimensional representations and mappings in terms of dynamics, and that are adequate at some scale regime that you're considering. If that were not the case, then I doubt that we'd be sitting here having this nice conference and having a good chat. There's a good indication that this is a property of our world, that our world can be understood in this way, is the fact that we are here and that we have survived so far and that our brains are able to function somehow. There's some theoretical evidence, because if the world was so incredibly complex that we would have to understand absolutely everything down to the microscopic level at all times, we would never get to eating a sandwich or doing some other normal thing. So there's theoretical evidence that this appears to be a property of our world in terms of successes of effective field theory, deriving simpler laws of what happens at some scale where you don't have to really understand all the microphysical interactions. And notions of emergence are related to this. So in condensed matter physics, you have phenomena that emerge from complicated interactions at a microphysical level, and that appear like new phenomena. But it is possible to derive them somehow from a theoretical point of view, and you don't need to understand everything at every level at all times to work. So to keep with the previous example, even though we don't have a good theory of quantum gravity, we can still drive our cars and use GPS without bumping into houses all the time. In the machine learning literature, I would refer to you, in case you haven't looked at it yet, to the essay by Stéphane Mallat, which is now 5 years old, on understanding deep convolutional networks, which is an attempt to think about why those networks seem to work quite well in terms of this hierarchy of scales and the types of quantities that you would expect a network with a convolutional architecture to extract. So, but let's retain this notion that understanding is about finding lower dimensional representations. So now comes the first technical point I wanted to make, which is related, which is that neural networks are universal function approximators, and that's a point that I've seen on several introductory slides. That's true, and the proof of it is in Sabenko in 1989. It applies to infinitely wide neural networks, by the way, so not typically the ones that we have in our computers, because our computers are finite. And it's often quoted as a good reason to use neural networks. It's a necessary condition, I guess, at some level, but in fact, by itself, it would be a good reason not to use neural networks for anything, because just by itself, the fact that you can build large neural networks to approximate any function would never have led to the widespread use of neural networks for any applications. Because it's easy to come up with universal function approximators, right? I mean, if you just specify a number everywhere on the real line, that's a universal function approximator. In the number pi, depending on how you code it, you can find any function you want. In the Riemann zeta function, there's every possible function is in the complex plane of the Riemann zeta function somewhere, but it's completely useless because you can't find them necessarily. So the much more important point is that neural networks with certain architectures tend to approximate useful functions. And again, the space of useful functions occupies a much lower dimensional subspace of that space of all functions, most of which are completely useless. So the keywords here are inductive bias, deep prior things that have come up, where we choose network architectures to help us select useful functions that solve our problems. Technical point number 2 is that, and this is very recent, so there's a paper out today, references at the bottom, is about neural networks are only good at interpolating. So this is kind of the opposite way. People that are critical of neural networks sometimes say, oh yes, neural networks just interpolate the training data. If you think about interpolation as meaning that you reproduce some function in a high in some space, within, let's say, the convex hull of all of your examples, then by the curse of dimensionality, in a sufficiently high dimensional space, any new point is going to be inside the convex hull of your previous examples with exponentially small probability. So almost certainly, let's say if you're in more than 100 dimensions of your input data set, and certainly for cases of image analysis and so forth, neural networks actually always extrapolate. The new examples that you're running on are always going to be outside the convex hull of any set of previous examples with extremely high probability. The only way that this can work, and this is my interpretation, this is not in the paper makes this technical point, is that this is if neural networks inherently find a much lower dimensional representation, a much lower dimensional subspace where the data are represented. And that, as I said in the previous slide, amounts to some level of understanding. So neural networks do somehow understand things. Otherwise, they would not be useful in all these interesting tasks that we see, where understanding is defined in the previous way. So the technical point number 3 is the point about that we talked about before, trust and understanding, and whether the two are the same. From a Bayesian perspective, posterior model probability, so whether you believe a model or not, is the evidence times the prior, right? Model evidence by itself makes no reference whatsoever to simplicity of the model or anything to do with Occam's razor. And if you are if you labor under the misapprehension that is otherwise, we should have a chat or maybe discuss later. But if enough evidence is accumulated in favor of a model, eventually, even if your prior, you might not like complicated models, so you can set your prior low, right? But eventually, with enough evidence, the posterior probability, which is the product of the evidence and the prior, will overwhelm any previous discomfort you might have about complicated models that will be in your low prior. Remember, for example, that so however small that prior probability may have been. So remember that many models are beautiful, simple, understandable, and wrong, right? So in that case, you want the complicated model to win. So the consequence of that is that we will eventually start believing, in the Bayesian sense, and that's similar to trusting, results obtained with machine learning, even if we do not understand them. So I think that's my final slide. Yeah. So machine learning starts with a training set, but we hope that machine learning should end with understanding, at least in our business and physical sciences. Important ingredients here are that you know what problem you're solving. The data are not everything. We've learned that because it's not just about interpolation. So the architecture is important. Thinking about how that relates to your physical problem is important. Building in possible symmetries, etc. Those are important things. Inductive bias. And the choice of the loss function defines your problem. So if you've always assumed quadratic loss and that's the end of the story for you, maybe you might want to think about whether there are loss functions that are adapted to the particular problem you're solving. Because that's, neural networks and deep learning is about writing down optimization problems that if you can solve them, solve your problem. And that's defined by the loss function. So that's very important. And François made a similar point in the first debate. So the other point that was mentioned by Bhuv is build physical non-black box analogies, analogs. Shirley's work is similar to that. It goes in that category. That are somehow benchmarks for your machine learning approach. So in work that's been done, that's being done here, and with my collaborators, this notion of doing Borg, interpreting large-scale structured data with sampling approach, with a fully specified forward model, that can solve certain problems where these machine learning techniques I talked about, they should also be able to solve that, and they should get the same result. And Borg is completely understandable and mechanistic, and everything is completely transparent. So then you have some trust that the machine learning techniques can also solve some kind of modifications of those problems that are no longer solvable by your non-black box approach. And then use machine learning surprises as inspiration for research. That's the ultimate path to understanding. And when a machine learning model gives you a result that you're surprised by, it probably highlights that your understanding is lacking somehow. And as Bhuv was saying, maybe that's a good motivation to invest those 18 years of research to get to the next level of understanding using good old science. So.
Thank you, Ben. So understanding is finding low-dimensional representation. The question is how to find them in these complicated deep neural networks. But maybe someone from the audience has an idea or a question.
So this is this is Niall Jeffrey, by the way. This is a question for kind of Ben and Shirley, as it links. I'm basically asking myself, what are the real problems of understanding in physics for even humans? And many of the big problems are things like interpretation of quantum mechanics in reality and cosmology, or even just understanding the laws of thermodynamics. So within the framework that you're thinking about these problems, in Shirley's case of thinking about graph nets, which I also love, can you imagine a situation where the understanding is not actually about interactions between individual particles, for example, or objects, but actually a kind of global understanding of principles like entropy, which don't seem to fall within the kind of understanding you've been talking about?
I'll let Shirley respond to that. I think that was addressed to her.
Shirley? Can we get Shirley?
Sorry, I just have to unmute and turn on my video.
We see you.
Yeah, now this is... Yeah, okay, this is a great question. Some of the work that Ben and I and Miles Kramer and our DeepMind collaborator are looking into are things that are related to this broad general question. And I think Ben was the one who really inspired us to think about, how do we look for lower dimensional representations like entropy, temperature, density, instead of the particle interactions. And I think Ben actually has thought deeply about this, and that's why his talk actually.
Yeah, I mean, the question you might want to ask a neural network is, can you derive some, similar to what I was mentioning in terms of having the right kind of description depending on the scale. If you start with a microphysical description, can a neural network abstract from that and derive some effective interaction that represents the system at a coarsened scale, which is related to your question about statistical mechanics, and can you, it's sort of the relationship in a coarse way, it's the relationship between kinetic theory and thermodynamics. We have some emergent description at the level of large-scale average quantities that you can derive from some smaller scale microscopic physics. And it will be interesting to see whether one can automatize that process at some level.
Please.
So there's been quite a few comments that would be worth checking. And among those, Jenny Wagner is wondering about your definition of information. When you say a machine finds information, she's wondering, so what do you mean by information here? Isn't information something subjective that you define as relevant features of your interests? Hence, do you think AI is only a tool for human-posed problems based on your final slide?
I would define information in the Shannon way, so where it talks essentially about how well defined how many bits you need to represent a certain amount of information, which translates into how the width, for example, of a distribution, or.
But you still have to say bits about what quantity, right? Not about everything of the world. So I think that might be how these two perspectives
Yeah, I mean,
fit
you can
together.
make it really precise when you're talking about it in the context of a particular physical model that is parameterized a certain way. Then it's a very precise definition, and you can use Shannon-type ideas or asymptotic ideas like Fisher information, like we've been talking about with these information maximizing neural networks that explicitly maximize like quantities. So then it's very well defined. When we're talking about more general situations, like I was hinting at in these slides, where there are some lower dimensional representations that are clearly somehow learned by the network, but that are not necessarily transparent or accessible for us, then it becomes much less well defined. But I mean, you could also say that when from the Bayesian point of view, information isn't the key thing; it's utility that's the key thing. So if you assign some utility, you make decisions whether you trust a model or not based on how useful it is for you, and so then you can. Now it's not always easy to define exactly what you mean by utilities. For example, if you want to build an experiment and that costs a certain amount of money and it shrinks your error bars by some factor, how do you match the amount in euros to the reduction in the volume of the constraint surface? So those are not, and it's not necessarily a linear function either. So those are not simple questions. Yeah.
But you can define information as a utility of not being surprised by something. Because if you go this route, you just end up by Shannon's information or Kullbach-Leibler divergence. Do we have a question? I would have one, but let's see. Yeah, here.
I have just a comment, a question, but a bit different. I was wondering how much of these fears and doubts we are expressing here regarding machine learning are common in history each time we have a change in technology. I wonder, I'm pretty sure people started to doubt when we started using computers to analyze photometric data instead of plates. And what do you, do you think it's something related to that? Because does it mean the fact that we're having these doubts, does it mean that in fact ML is actually important?
This is related to the previous sociological statement about science advancing one funeral at a time, right? So there will always be some holdouts, people that will never change their mind. Eventually, if it's really useful, those people that think it's natural because that's the first thing they learned, will move the subject forward.
Actually, I think I think there's a slight difference. It is a new technology. It allows us to do stuff that we couldn't do before. But there is a complexity in this technology. Okay, we're talking about understanding, and well, we can't. We have ways to say, oh, this thing is happening here. Maybe it makes sense. Okay, but I think it's extremely hard to interpret and to understand this technology. You can run it. It's easy now. We have toolboxes and everything, but really understanding what's happening, that I think that's the key why people are afraid, and not only in astrophysics, for society in general.
Yeah, that's a very important point. I think it's especially the discrepancy between the ease of utilization, and anyone with an internet account can run things that are that would have been considered absolutely magical 20 years ago, and the difficulty in understanding what's actually happening. And so I guess that disparity, that tension is, it's like, it's very easy to light a whole bunch of gasoline on fire, but should you?
Yeah, I would just like to say, the thing that happened, of course, with the arrival of photographic data was that there was all of a sudden there was too much data, and another paradigm needed. Computers needed to be invented in order to analyze the data from the photographic plates.
So to pick up on a point Henry made earlier, that yes, I think it is, of course, healthy to be afraid of machine learning. But one way that advance happens is that if there's any kind of qualitative new finding, we are in this data rich regime. So there's going to be a next bigger, better data set that will be able to verify or refute a finding made with a previous data set.
Yeah, absolutely. So this is, I think, where this evidence calculation comes from. So evidence is basically about predictions and verification of predictions. And so if you can predict the posterior distribution for next year's survey from this year's survey by using these techniques, and that happens year after year after year after year, then at some point people are going to not wait for a year. And that's the point about eventually the evidence then overwhelms the prior, however small it may be.
Yeah, I have a question. So your point of finding a low-dimensional representation of something complicated. Rémi, in your methods you mentioned in order to look at the interior of neural networks, is there something which is suited for digging that out? Finding what could be the generalizations the neural network has made in order to actually predict things which is out of the convex hull of the examples it saw? Oh, you can say no.
No, I don't really, no, I don't have ideas.
But for my feeling, that would be the thing we need in understanding AI. Maybe a bit more than, say, in feature maps. Or Ben, do you have an idea how to?
So for a practical example would be, let's say we did, they're very clever and interesting methods for anomaly detection, for example. They typically have something to do with learning a lower dimensional representation of a model based on examples, where the lower dimensional representation is actually visible in the latent space, for example, if it's an autoencoder. But I'm almost certain that if you did this with a particular cosmological data set and you then showed it some real data and you were really excited because you thought now it's going to show you that cosmological effect, that undiscovered cosmological effect, I am almost 100% certain that the first n times that you do this, you will just find some noise fluctuation or you'll find some systematic because all of those degrees of freedom are going to play a role.
Even worse, you're going to find a subspace, but your effect that you're searching for is hidden somewhere in this subspace, and you don't know where it is anyway. So you simplify the problem, but you still have to search for it.
But how would it represent it? So that basically in some layers, a network is only basically, if you have n neurons in that layer, and so in n-dimensional space, it only goes into a small, low-dimensional manifold of that space, right? There must be methods to search for that, right? If you run the network 1,000 times with data, and then you monitor whether some layers, or maybe a sequence of layers, is just sampling some suborbit. I think in chaos theory of orbits, people have used methods like that.
Yeah, but there's always going to be some aspect of your model. If you really just run it on actual data, on raw data, there's always going to be, there's so many layers in the graphical model in terms of, some photons arrived, some cosmic ray hits.
Sure, it will be noisy. That's clear.
Something warmed up slightly on one particular orbit of the satellite, and all of that. Maybe it's actually useful. I mean, those are useful things to discover. But I think the first things we'll discover in many cases are going to be such things, and not necessarily the next breakthrough in.
Search for the bias in your data and in your model. That's one of the points I tried to make. It's extremely important, and I strongly agree with you. Surprises are the most important. I mean, if you say, I'm going to use this model, and you play with it, and it works, well, you're going to get a paper. But, I mean, if you play and you get a model, and you say, why? What's happening here? There is this weird stuff happening, and maybe you're going to find something. Well, both maybe physics but also in machine learning, because if you expect something and it does not work like that, well, come and tell us. We have NeurIPS conference and everything. And we love physics papers, actually.
Yeah, I think in cosmology we are used to that situation that one starts with random findings, well, Hubble constant 50 or 100, and then we zoom in. But we have a question up there.
Yeah, I have I'll speak a bit more hypothetically. Yeah, sorry. It's Marko Shintov. So I'll speak a bit more hypothetically and maybe futuristically. So, I mean, do you think that it's maybe an unbridgeable gap, this interpretability, understanding of machine learning algorithms by humans, that simply our brains are maybe just not designed in the way to understand what machine learning algorithms or AI at this point can understand? In the same way that even discussing simpler theories like Newton's gravity with, dogs, for example, just won't take us much further. So do you think if machine learning algorithms and AI left on their own devices are able to infer something more about the universe, and if let to do their own business, can help us devise new technologies and come up with better solutions about the world, about the problems in the world, but we cannot understand them? In the same way, for example, that GPS has made our lives much easier, even though that most of the people on Earth don't understand general relativity and don't understand how GPS works. So in the same way, maybe AI has a lot of help and solutions for us, even though we cannot understand it. So this would be more to the benefit of the society and not really for fundamental science, because the goal of fundamental science is more of to understand what's going on in the universe, with the ultimate goal to use these laws of nature to basically make our lives easier. So yeah, do you think that we should let machine learning and AI algorithms do their own business and help us essentially come up with better solutions to our problems? Or do you think there should always be a human in the middle and to do the interpretability at the cost of limiting their potential?
I think that's a perfect question for a last round of statements by the panelists. And maybe in the order they gave presentations, or backwards.
Okay. So again, that's a difficult question. I think the problem here for what you're talking about is acceptability. And actually, it's exactly the problem we have here. That's what we're talking about. We talk about understanding, but actually the question is, are we going to accept those models? Are we going to accept the prediction? Will we trust them in the end? Sorry. Oh. So you come back tomorrow? No, I'm talking about acceptability even for machine learning, in general, even in society. Okay? Well, machine learning is a tool. The specifics of this tool is that it is hard to understand. Well, the more useful a tool is, the more we're going to use it anyway. I don't have...
Okay. Shirley?
I learned something that, from my graduate school advisor, that it's important to know what the other person wants. And I think in this case, we want to know what we want here. And as scientists or computer scientists, you might want different things. Some of us might want to actually understand what the machine really learns. Some of us might just want to understand enough that we can trust it to learn something else that we want to actually learn. So for me, in this case, maybe I want to learn about the fundamental parameters of the universe. And all these are just tools and pathways to that goal. In this case, I think the level of understanding might be required as different. Like what Booth was suggesting, as long as doing it correctly with these, say, blind challenges or not blind challenges, do we really care? I think Yannick famously says something that if the doctor, like a human doctor, is only 85% correct and the machine gives you 95% correct prediction, which would you do? or trust or use. So I think it depends what we really want at the end.
Okay, thank you.
Thank you. So in keeping with my kind of concrete mode, I wonder if, applying machine learning codes as black boxes to get powerful results will feed back to the, long-term dream of cosmologists of coming up with some analytical transform that tells us everything. There's this idea that if you use a log normal transform to a nonlinear field, you recover a Gaussian field. So maybe such physical analytical approaches will get a boost from the existence proof of these field-based machine learning methodologies.
Okay, thanks. Ben? Famous last words.
The question is an ethical question, because once you start talking about the benefit to society, then defining your utility, what you decide to do has ethical implications, and I think that goes a little bit beyond. Those are very important, but I don't think just scientists should decide that. When it comes to what scientists are interested in, like Shirley was saying, we typically want to understand, we typically want to advance the field. We have certain goals in, that we call understanding. For example, do we understand what the dark energy is doing? Do we understand what dark matter is? Those are open questions that we are interested in as cosmologists. If the machines can help us make headway, and if they are like the AI doctor that's doing better than the human doctor, then I don't think we can avoid them being used. I think that's a logical consequence, so the other quote is, I for one welcome our AI overlords.
Okay.
But maybe that should not be the last sentence.
No. We can vote for this, but I think understanding is overrated is still the sentence of the day. Or let's see who wants to have this as a sentence of the day. I see a 4. Who wants welcome the AI overload? Oh. Okay. So the winner of this competition is Ben Wandelt, but nevertheless, let's thank all the 4 panelists for an excellent discussion.